Welcome back to elementary statistics. In this video, we're going to be talking about the shape of a distribution. Previously, we've talked about two different kinds of distributions. A categorical frequency distribution is used when we're describing data that is discrete, sometimes discrete numerical data, sometimes qualitative data. We also talked about a grouped frequency distribution, which is more useful when we have continuous data and we have too many distinct data points to think about each one individually or each possible value of the data individually. When you have a categorical frequency distribution, you can use tools like bar graphs and pie charts in order to visualize the data. When you have a grouped frequency distribution, we need a slightly different tool. And that's what we're going to be looking at here today. So let me get my head out of the way. Oops. Let's use the thin pen. All right. And let's say that we are taking a sample of men's heights in inches. And the data is actually going to be given to us with the mean and the frequency. So the average or the central value for each class as well, along with the frequency. And then once we have that written down, so height of 58 inches has a frequency of 47 occurrences. A height of 61 inches has a frequency of 56 occurrences. 64 inches, 65 occurrences. 67 inches, 73 occurrences. 70 inches had 62 occurrences, and 73 inches had 49 occurrences. With this information, we can kind of work backwards to try to figure out where the class boundaries had fallen on this distribution. Doing this is not strictly going to be something that I ask of you, but it's again something that is worth thinking about. So if I have a midpoint of 58 and a midpoint of 61, well, the middle between those is between 59 and 60, so and between 61 and 64, looks like 62.5 was the midpoint there. And then we realize that we're really just counting by threes, right? The midpoints are increasing by three, so the boundary points are going to be increasing by threes as well. All right. And so we have some class boundaries here. Again, I'm probably not going to ask you to produce class boundaries given the midpoints like this on any problem on your own, but I wanted to show you that the reasoning is possible. It's a skill that's worth having some familiarity with. It may come up for you at some point in the future. Once we have the class boundaries, either because we were able to figure them out or because they were given to us, we can use those to produce a chart called a histogram. A histogram looks very similar to a bar graph, but there are a couple of key distinctions. The most obvious distinction is that a histogram is used for continuous data. A bar graph is used for distinct data, discrete quantitative data or qualitative data. The other thing about a histogram is instead of labeling each bar individually, we actually label the endpoints. So that's why having the class boundaries was important. For the sake of space, I'm only going to label every other boundary, but we get all of the boundaries going across here. I hope I left myself enough room. So 56.5, I don't have enough room to write 59.5, 62.5, 65.5, 68.5, 71.5, and 74.5. Right. On the horizontal axis is always our x values, and on the vertical axis is always our f values. The variable x can change depending on the context of the particular thing that you're looking at, but we're generally going to use x in this course because it's a generic, this is the thing we sampled, and talking about where the samples come from is an interesting idea, but generally not something that I worry too much about in this course because once you have the data, analyzing it works the same no matter what data you had in the first place. So our largest frequency is 75, and I'll use that to help inform how I'm setting up the vertical scale here. Looks like counting by 15s might be the way to go. Counting by 12s might have also worked. The horizontal scale on this one, we talked in the previous video about some ways that graphs can be misleading, especially when it comes to breaking the scale. On a histogram, you have a horizontal scale and a vertical scale. Breaking the horizontal scale is usually not a big deal, as we did here, right? The first data point is at 56.5, which, the space between 0 and 56.5 is much smaller than the space between 56.5 and 59.5, but that's okay because you don't lose any information. You're not getting anything from the horizontal scale. It is still important that the vertical scale be reasonable, and a reasonable vertical scale always starts at 0 and has equal spacing. Right? So that is something we always do want to watch out for and pay attention to. On the horizontal scale, once we do have the scale set up, once we do have our starting point, the space between each tick mark should be an equal space and an equal value, right? The interval between two sequential tick marks should represent the same distance, and it should be the same physical distance so that our histogram is done fairly. But now that we have that, again, we're going to draw our histogram in the space in the middle. So between 56.5 and 59.5, we had a score of 47, frequency of 47, which is somewhere in the general vicinity of there. Between 59.5 and 62.5, we had a score of 56, which is in the general vicinity of there. 65 is somewhere about here. 73 is right about there. 62 is here or somewhere thereabouts. And then 49 is something like that. All right, so unlike a bar graph in a histogram, the bars are all pushed right up next to each other to again emphasize that the data we are looking at, the data we are graphing here, is continuous data. We generally don't worry that much about the internal boundaries. It's the top that is the difference. Shading in the entire histogram in one color is perfectly reasonable, but I'm going to go ahead and hash it with diagonals going in opposite directions to help draw your attention to the uh, different bars. Producing a histogram compared to producing other types of charts that we've talked about is fairly straightforward. It might be something I ask you to do pencil and paper. It's worth doing one or two examples by hand to make sure you understand how it works. But it is, again, something that is relatively easy to do without too much thought. Related to the histogram, let me copy this frequency table. Related to the histogram, there is another type of graph that is often used for grouped frequency data like this. It is called a frequency polygon. This particular set of data is not a good application of a frequency polygon because there's just not enough data. Frequency polygons are useful when you have many classes in your frequency table. Um, on this frequency table, I can do some quick arithmetic. 47 plus 56, 65, 73, 62, 49. Those are all pretty close to 50, a little bit beyond. So 1, 2, 3, 4, 5, 6 classes. Each one has about 50 members in it, a little bit above 50 members for most of them. So maybe 7 times 50 is 350. There's a quick estimate of the size of uh, this distribution, the number of data points in the distribution. 350 data points in 6 classes is relatively small. That's not a lot of classes. We could have expanded this out and gotten more data, but that's not what happened. When you have many classes, when you have 12, 15, 20 classes, a histogram is still the tool of choice. When you have 100, 150, 200 classes, because you have that much data, that's when a frequency polygon really becomes the more useful tool. Right. But a frequency polygon, again, is going to have our x values at the bottom. Our f is the vertical axis. And the frequency polygon does work on the midpoints. So 58, 61, 64, 67, 70, and 73. All right, I managed to draw this graph a little bit taller, so I guess I'll count by tens this time. And if the histogram is the continuous analogy of a bar graph, the frequency polygon is the continuous analogy of a broken line graph. And in fact, with this few number of classes, it really looks like a broken line graph. If there were more classes, you would start to see this become a nicer looking curve. Right? Put your dots in, connect the dots, and you get a curve that looks like that. It's the same idea, it's giving us the same data. But again, frequency polygons, very useful when you have a lot more classes, especially when you have more classes than you can fit as individual tick marks going left and right. All right, so I'm not even going to try to set up a set of data to go with this because it's just going to have so many entries in it. But the value of a frequency polygon is when you start to get so many individual little bars here that even though each little bit of the polygon is a straight line, because they are all so incredibly tiny and so close together, it starts to look like a smooth curve. Right. If any of you have happened to have taken calculus or will be taking calculus in the future, this idea of taking a bunch of straight lines and turning them into a smooth curve is the entire idea of calculus. No, I'm not going to be building on calculus in this course. That is basically as far into calculus as we're going to go. There's one other place later on in this course where I'll show you a formula that's used that is something that is a lot of fun in calculus, but we'll skip all of the calculations and I'll give you a look-up way of solving the formula without doing any of the nasty calculus work that goes into it. Right. So when you have enough categories or enough classes in your group frequency distribution, um, your frequency polygon starts to look like a smooth curve here. That's where the frequency polygons start to become useful. We're not really going to get into anything where that is going to happen in this course, but I like mentioning that that is a thing because it also gives us an easy tool for analysis. Right? Trying to produce a frequency distribution, a table that gives us information in a shape that is interesting, is tedious. It takes a lot of writing, and honestly, you don't get a lot from it. Drawing a histogram is tedious. It takes a lot of writing. You don't get that much from it. You get just as much from a frequency polygon, and you can draw them very quickly. So that's the biggest advantage that frequency polygons are going to have for us. I'm going to give you several examples, in fact, 8 of them in quick succession for the rest of the video today. And a couple of times throughout the rest of this course, you'll see me draw a frequency polygon as a smooth curve like this to give you the idea of what the shape of the distribution looks like without having to get into the details of the actual values of the distribution and what the actual histogram looks like so we can avoid drawing all of the bars. It's just going to make taking notes and getting into the interesting discussion happen a little bit faster. All right. And I want to be able to talk about the shape of a distribution to talk about this idea called skew. Skew is a measure of how centralized is the data in the distribution and asks the question, are there any outliers? And I said I was going to draw 8 frequency polygons in very quick succession. So let's get into drawing a bunch of frequency polygons in fairly quick succession. You may want to wait until I've drawn all of these so I can start talking about some of the characteristics that are important so you can make sure that your drawings actually highlight those same characteristics. Your frequency polygons certainly are not going to look the same as mine, but they should give a pretty good picture of what's happening. Right, so there's a couple of coordinate axes. Let's draw a couple more down here. All right, so here are my 8 distributions. The order that I talk about these is going to be a little bit hit and miss, but let's talk about the one that I drew on the top left. This is known as a normal distribution or a bell-shaped distribution. This is the standard by which all other distributions are judged. We will see as we go through this course that most of the time when we collect data, we're going to find that our data falls into this pattern where most of the data is clustered near the center and the frequency quickly tapers off in either direction in a mostly symmetric way. All right, so clustered in the center, tapers off in either direction, mostly symmetric. The second most common distribution that we're going to look at or that we're going to encounter in this course is this one over here, which is known as a right-skewed distribution. What I want you to notice in a right-skewed distribution is that we've basically taken our normal distribution and just grabbed the right-hand side and stretched it out. All right, so we take our normal distribution, right? If you just look, oh, there we go. Yeah, my camera can't quite reach, but if you just look at this part of the distribution here, it looks normal. But then I grabbed this tail and I just dragged it. All right, another way to describe a right skewed distribution, sometimes you'll see it called a positive skew. And the thing that I like to think about is that this is a distribution that has high outliers, right? All that extra stuff in the tail, that's the stuff that's interesting. That's why we talk about this being skewed to the right. The one right next to it is the mirror image of that. So instead of grabbing the high tail, we grabbed the low tail and dragged it out, giving us what's known as a left skewed distribution, sometimes called a negative skew, and a distribution that has low outliers. All right. These three distributions are really what we're talking about when we talk about skew. The other distributions, sure, we can use skew to describe them, but those pictures are the picture of skew. There's a mathematical formula that you can use to calculate skew and assign it a numerical value. That's not something that I'm all that interested in. You're not going to see it in this course, but it does exist. And that's where the positive and negative comes in. When you perform this calculation, if you get a number that is um, positive, I think usually it goes from -1 to +1. If you get a number that's positive, we call it positive skew or right skewed. If you get a number that's negative, we call it negative skewed. And if you get a number that's very close to 0, well, that's where the normal distribution comes in. Jumping around a little bit, I want to look at the two distributions here on the right. Which are called the J-shaped and reverse J-shaped distribution. These are left skewed and right skewed taken to the extreme. Take the left skewed data and drag that tail out so far that it becomes a completely descending or completely ascending, I guess, set of data. And to talk about that, we can call it J-shaped, we can call it reverse J-shaped. If you still referred to these as being right skewed or left skewed, you wouldn't be wrong, but we can be a little bit more specific. The last one on the top row is known as a flat distribution for very obvious reasons. A flat distribution tends to be fairly symmetric. It tends to, unlike the normal distribution, it doesn't taper off. It stays about the same everywhere. All right. Then up next, we're going to talk about this guy, which is known as a bimodal distribution. When you're looking at the bimodal distribution, what I want you to look at is what would happen if I cut this graph into two pieces. Each of those pieces looks like a normal distribution. That's the characteristic of a bimodal distribution. It looks like there are two separate normal distributions that are smacked right next to each other. In a very near future, we're going to be talking about the mode of a distribution. We'll give a more specific classification to this. But one of the things that I do like to mention about the bimodal distribution is that it doesn't actually have to be equal height peaks. A fairly common distribution is one where you have a small peak and a large peak, or sometimes the mirror image of this. But the fact that you have a peak and you have another peak, and there's this dead zone in the middle where you have very few um, data points is the key feature of a bimodal distribution. And then the last one is called U-shaped for obvious reasons. Just like the J-shape and reverse J-shaped, it is perfectly reasonable to call this a bimodal distribution, but it's a bimodal distribution taken to the extremes. The peaks are so tall and the valley between them is so little, and there's no or almost no taper off at the endpoints. So it just takes a normal bell curve and flips it upside down. That kind of extremism is very rare in data. It's not something that you see all that often, but it is something that can exist, and having a separate name for it is a nice idea. All right, so again, I want to stress that there are ways of calculating skew. There's a mathematical formula involving some measures of central tendency that we'll be talking about in the next couple of lessons that gives you a formula for naming the skew of a distribution. I'm not that interested. Being able to calculate skew doesn't really gain you anything. It doesn't give you a way of going on to test hypotheses, which is really the big idea that we're looking at in this course. If you go on to study statistics in further detail, it's probably something that's going to come up and be useful to you at higher levels of statistics. But if this is your only statistics course, then this is just a picture matching game. Look at your histogram or your frequency table, look at the shape of it, and try to figure out which of these shapes is the closest match. That's all we're doing. But having that is going to give us some very good information. Different distributions have different ways of talking about them. In the next few videos, I'm going to be talking about the idea of central tendency. What is happening in a distribution on average? It turns out that if you have a normal distribution or a flat distribution, there is one tool for central tendency that tends to be more useful. If you have a skewed distribution, you tend to want a different tool. And a bimodal distribution tends to want a different still tool for talking about the average. That's a gross simplification. Certainly, depending on the context, depending on what you are looking at, there are other considerations to take into account. But that one picture alone is an important data point. Know what the shape of the distribution looks like and use that to try to figure out whether your tool is actually going to give you a good result. The bimodal distribution, I have a very good story on, which has to do with life expectancy. I think I have enough time in this video to talk about it here. You may have read in a history class that early colonial America was very harsh and the life expectancy was very low. I've seen reports that average life expectancy of a person born in early colonial America was 21, 25, somewhere in that regard. The interesting thing is that if you look at records, I am really blurry. Let's try to make me less blurry. There we go. If you look at records of leadership and property ownership, despite the fact that the average life expectancy was 21 to 25, somehow the leadership of these early colonies were all in their 50s. and people were dying in their 60s and 70s. So something is weird here. And the thing that's weird is the shape of the distribution. Actually, let's try drawing this a little bit more carefully because that went way too big. That's a little bit closer. The average age at which a person died in early colonial America has a distribution that looks something like this. And there's a peak here at age 2, and there's another peak here at age 60. People dying at age 25 is actually kind of here at the bottom where it never happens. But if you try adding all of the age of deaths together and divide by the total number, the tool of average that you learned since elementary school, well, that's where it puts you. Right? The average colonial American dies at age 25, but no one in colonial America dies at age 25. Everyone dies in the first 2 years of their life or lives to a natural lifespan, dies in their 60s and 70s. That's why looking at the shape of the distribution is so important and so valuable. All right, before I wrap up, there's one other tool for looking at the shape of a distribution that I need to talk about. And this tool talks about, instead of the frequency tables that we've been dealing with, what's known as a cumulative frequency table. All right, so here's that same set of data that we've been looking at. And let's extend it out and get one more column. So that our cumulative frequency table has this last column for cumulative frequency. Cumulative frequency asks you how many scores are there or lower. So in this case, we're actually going to take the upper bounds of our classes, and the first entry is going to ask how many scores are 59.5 or lower, and there are 47 of them. The next one is going to ask how many scores are 62.5 or lower. Well, all 56 of these that are between 59.5 and 62.5, and all 47 that we've already talked about, all of those fit into that category. So 56 plus 47 is 103. Then lower than 65.5, we take 65, we take 103, we add them together, and we get 168. Then 241, 303, and 352. And when we have a cumulative frequency distribution, we can form a type of chart called an ogive. In an ogive, our data across the bottom is going to be the upper bounds. Instead of the midpoints or the entire boundaries, we're only looking at the upper bound. And one of the interesting things is we actually have to start at 0. And so the ogive gives us the data presented in this format. So we can see how far we have to go to get to a certain percentage. All right. Once again, an ogive isn't something we're going to use all that much in this course, but it does have a couple of applications, and I feel like it belongs with the rest of this, so I wanted to mention it in this video. As you're looking at this, the way to think about an ogive, again, is that cumulative idea. Think about this vertical scale. Very often when we use these, it's going to be a percentage. So if we want to know how far into the distribution do we have to get before we've hit at least 60% of our data, we find that 60% score, we go over to the ogive, we drop down, and we read the information from there. All right. It's kind of a niche thing, but it is a thing that can exist, and so it's a thing that I wanted to mention. All right. All right. Last up here, a point of discussion. When we talked about grouped frequency distributions in the first place, I gave you that general rule of thumb of take the square root of the number of individual data values in the distribution and use that as your starting point for determining how many classes to include. I said at the time that determining the number of classes to use for a grouped frequency distribution was more of an art than a science. Now that we are looking at the shape of a distribution and we have some tools for talking about what a distribution looks like, I want to follow up on that discussion. Can you think of anything that could be a problem if you construct a grouped frequency distribution and you use too many classes? How could that negatively affect your histogram? What kinds of things would you be looking for to determine that that is what happened? Or what about too few? If you use too few classes, how could that negatively influence your histogram or any of the other tools that we've talked about so far? If you have any thoughts on that, I'm interested to see you share them. Otherwise, I'll wrap up here and I'll see you in the next video.